Let's find a set of vectors in Rn that will span all of Rn. Can we do that? It's not hard, but I'm asking you, it's quite easy. Maybe that's why you're puzzled. So can we find vectors? Let's call them v1, vn. Such that any v in Rn can be written as follows: as combination of some coefficients, let's call them lambda, I v I. I go from 1 to m. Let's do it in a simple case, in R2. Yeah, let's do it in the simplest situation. That is not completely trivial. Let's do it in R2. Yeah, let's do it here. Can you find two vectors in R2? Or 3 or 4? It doesn't have to be 2, okay? 1 that will span all of R2. Let's take two vectors in R2. Okay? Let's take 1. Okay, so the simplest vector I think of is 1, 0. Okay, there's a notation for that. We call it also E1. Right? So the vectors of this form are called EK, yeah, where the kth entry is 1 and all the other ones are 0. Right? So E1, does it span? Does this span of E1 equal R2? What is the span of E1? If you have only one vector, the span is easy. You just multiply that vector with any scalar, right? And you get all the scalars of the type. So what is this equal to? This is lambda 0. So lambda R. Is this equal over all of R2? No, because I can never get elements that have non-zero second coordinate. Okay? So this is not true. Okay? That's not true. So span of E1 is not enough. Can you find another vector in R2 that will span 1, 1? Okay, so for example, you take 1, 1. Okay. Now here we have two vectors. So let's show this one is V1 just to conform with that notation. And this one V2. Will V1 and V2 together span all of R2? Yes. How come you're saying yes? What did you do to this side? Yes.
Because we can, if we trace it in the parallel way, it forms again a plane.
Yes, but you're being very intuitive here. Okay, so let's satisfy our definitions. Okay, it's correct. What you're saying is correct. Okay, sometimes the difficulty with this in the algebra is to make sure that we're not saying something which we know from experience without having proved it mathematically. Okay, so we just want to check that what you're saying is correct mathematically. So in order to do that, what we want to do is we want to check. So claim. So what you're doing is very important because it's exactly how you can formulate a reasonable claim. Okay, and then you want to check that it's true. Okay, so claim that here we want to claim the following: the span of V1, V2. Okay, I'm going to write it in a formula matrix because it's just going to be easier. Okay, is equal R2. Yeah? So this claim turned out to be wrong. Okay, so now I'm going to do it like this. Okay, so from now on I'm going to always take square brackets around the span because I'm going to only work with finite finitely many vectors. Okay, so they're just going to order them. It doesn't matter. I could have taken also v2, v1. Okay, we can show that after permutations the span doesn't change. Okay, that's not very important. The important thing is to try and show this. Okay, so my claim. Let me show that. Show that. We want to show it's enough to show that for any vector v in R2, I can find two coefficients for lambda 1 and lambda 2 in R such that V can be written as lambda 1 V1 plus lambda 2 V2. In other words, it means exactly the same thing. Okay, I'm just going to translate this into matrix vector notation. It means this. It means that for some vector lambda in R2, I can show that capital V, this is little v, okay, I mean, from my little v's, so I can distinguish them on the board from the capital V, okay. So can I find lambda 1, lambda 2 in R such that this is true? So in other words, can you solve linear system V lambda or V for lambda? So you always solve for some variable. Okay, so here we're going to solve for lambda. Can we solve this for lambda? So what is V here? Remember, V is the matrix with columns V1 and V2, right? Because that's what we're doing all along. Okay, so that's why. So can we solve this system here? Mind you, for any V1, V2, not for some V1, V2. So V1, V2 is given, okay? And you want to find lambda 1, lambda 2. Can you find this solution to that? Yes, why?
Because it's a linear combination.
What is the linear combination?
The lambda 1 V1 plus lambda 2 V2.
Yeah, let's do it. Let's do it without confusing ourselves with too many sophisticated things. Okay, this is like a 2x2 system. Okay, let's solve it.
No.
Come on, let's solve it. Imagine V1 and V2 are given. Okay, and solve it. How would you solve it? Well, you do back substitution because it's triangular, right? It's easy. So you just solve it for lambda 2. Who will you take lambda 2 to be? It's V2. Okay, so solution would be take lambda 2 to be V2. Okay, and lambda 1. That's the only non-trivial bit. Okay, lambda 1 has to be equal to V1 minus lambda 2, right? Which happens to be V2. Okay. And V1. Okay. That's the solution. Right? So any vector V1, V2 I give you in R2, you can always write it as a linear combination. So yes. So span V is indeed R2. Okay? And how about Rn? Now in general, for Rn, you see what we did here, we found basically a spanning set by adding a 1 here. Okay, that was your idea essentially, right? You said we have to do something with the second coordinate. Okay. Then you think about it, this 1 here, we could also have done away with it, right? Could have chosen 1, 0, and 0, 1. That would have worked as well. But there's something even more natural about that choice, right? Because you ignore everything else, you just look at the next coordinate. Okay? So in Rn, we could have done another procedure. So another choice for spanning set. For spanning. So R2 could have been E1, E2. Okay? Well, I remind you, EK in general is the set of vectors. It's the set of it's the vector formed by the all entry zeros except for the kth one, which is non-zero. Okay, so in other words, the coordinate EK R is simply equal to 1. I is equal to K, 0 otherwise. Okay? If I is different than K. That's basically what these E's mean. Okay? So we use this notation. This is pretty much kind of like almost standard notation in all linear algebra texts. Okay? So another choice for science could have been E1, E2, where and in fact, this happens also in Rn. You may pick so this is a very natural choice in Rn, okay? And this is also known as the natural spanning set, okay? So this set here is also known as the natural spanning set. Okay, so it's just an example. Good. All right. Now let's come back to our theorem, okay, and start seeing how we could. So before we prove it, we want to prove a small lemma. Okay, maybe before we prove that the big theorem there, okay, we're going to prove a lemma. And in order to keep the statement, I'm going to start the lemma here. Yeah, so. And another nice thing that we can do is think about the question whether this is a basis, right? So we know that it's a spanning set. We just showed it somehow, like we did it in 2 dimensions. A good exercise would be to show it in any dimension that is a spanning set, right? Is it a basis? Are the vectors E1, En linearly independent in Rn? It's something nice to think about. What's your guess? So can you find coefficients? Linear independence means this. Okay, can you find coefficients lambda 1 that would make it 0? That would make the linear combination lambda 1 E1 plus lambda 2 E2 all the way to lambda n En equals 0 without all the lambda 1s lambda n to be 0. Is that possible? In other words, can you solve the system matrix that has columns E1, En? What is the matrix that has columns E1, En? That's a matrix that has 1s on the diagonal, 0s everywhere else. Okay, it's the identity matrix. So Can you find lambda such that I times lambda is equal 0 without lambda being 0? No, because by definition of identity, you see it very quickly. It means lambda n equals 0, lambda n minus 1 is equal 0, all the way to lambda 1 is equal 0. You don't even need to do back substitution. It's already diagonal, right? So in fact, the only possible way to make a linear combination of these vectors equal 0 is to take the coefficients to be 0. And therefore, this is not only a spanning set, but it's also linearly independent. So this is a basis. Okay, that's what we're aiming at. Okay, so this is right, but it's not the only basis. That's the nice thing about linear algebra, that it's not. We're not doing trivial things. Okay? Because if this was the only basis, then we wouldn't have linear algebra. But there's many other bases in Rn. And there are vector spaces that are not necessarily Rn, and then understanding what the basis there is becomes a bit trickier. So let's do that as a small example before we continue. Okay, so example, another example. In let's say P3. Okay, so P3. I'll remind you what P3 is. Okay, so sometimes also we write it as P3R. Okay, so this is the set of all polynomials of degree polynomial of degree less or equal than 3. Okay. So let me remind you very quickly. How do we sum two polynomials? So what is a polynomial of degree 3? Means something. It's an expression of this type. It's a0 plus a1x plus. I'm going to write it completely because it's a cube. Yeah. So I'm going to write this. Okay. So how do you sum two polynomials? So suppose you have this polynomial here and this polynomial. Okay, so this one will go b0 plus b1x plus b2x squared plus b3x cubed. Where x is just indeterminate. Okay? So we don't, indeterminate means we don't have to worry too much about x. Okay? X is just something that satisfies the rules of algebra. Okay? So we're being just formal. Okay, so of course you guys know that polynomials are very useful things that you can use them to do lots of things, for example, to define functions. Yeah? But for now we're just using the formula. Okay, so how do you sum two polynomials together? Can you sum two polynomials together? Well, you go coefficient, you match the powers, right? Yeah? So what is the sum of p plus q? P plus q as a polynomial. Okay, so as think of this being one object, yeah? So p plus qx, which is also sometimes written as px plus qx. Okay. And by definition, the following up, it's basically it's a0 plus b0 plus a1 plus b1x, etc. Right? Right? That's the sum. Can you scale a polynomial with a coefficient, with a real coefficient? So can you do lambda? Also sometimes written as x. What is this? This is simply lambda a0 small plus lambda a1 x to the power 1 over lambda a3 x to the power 3. Okay. Let's find the spanning set. So of course, you'll have to check that these operations satisfy the basic axioms for vector space. This we've already done. Yeah, this was in the previous example. We've already done. But just in case you missed it, all you need to do is to show that these satisfy the 8 axioms of the vector space, meaning that it's an abelian group with respect to plus, and it satisfies associative and distributive and identity rule for the scaling. Okay, of course, this is for lambda. Yeah. So let's find the spanning set for this vector space. Okay, so now that we know that it's a vector space, let's try and find the spanning set that is finite. So basically, let's find. I don't know if it's possible, okay, but let's find. I don't know, like I'm going to call them P1 all the way to Pn. Because we also do powers here, okay, so let's be careful. And let's image them with a small bracket, okay, just so we know that this is not power. It's not algebraic power. This is just like a superindex, okay. So let's find these polynomials P1, Pn, such that if possible, okay, I don't know. First, we have to find n. We have to find that any polynomial. So it's for any p in P3. We may write p for x as being some combination lambda I times p. For r going from 1 to n. Pix. Okay, so that's next. Can you find such polynomials? Well, look at the expression. Just match this. I mean, this in general, this is going to be just a0 all the way to a3 x cubed. You're asking yourself, can I find polynomials such that this expression here is equal to that one? Well, there's one natural choice. Okay, natural in the sense that it's almost jumping to you from this expression here. Look at it. This expression here is a linear combination. If you assume that you're not doing the powers, so the powers are kind of given to you, okay? You're not allowed to multiply because that's not a linear operation, okay? But suppose that someone has multiplied for you and given you already the stuff multiplied for you, okay? So x cubed, x squared, and x power 1, and this is x to the power 0, in fact, yeah? If you want, yeah? Then you already have 1, 2, 3, 4 polynomials, very special ones, called monomials, okay, that you can take linear combinations of, and in fact generate all the elements of E3, okay. So almost by definition, E3 is given as, yes, pick the following, Prx dx to the power r, right? So, at this point, you see by definition. Okay. We have P3, in fact, is the span of 1 x squared and x cubed, right? That's basically what it is. In fact, another expression for another way of writing this space is also to write it as R people write it as R of X, and then they say something about the degree of polynomials, okay? Where X is just an indeterminate. You see, so I never used X in any kind of concrete way. Okay, that's why it's called an indeterminate. It could be anything that can be multiplied and taken the power of. Yeah, anything that you can take powers of will work for you. Okay, so what you're really focusing on here, the main thing, is the coefficients of your. Of course, this is not the only spanning set. Okay? You can have other spanning sets. Okay, you can have many spanning sets. Okay, so one spanning set is one choice. Okay, but you can have many other spanning sets. Okay, for example, you will see that polynomials can have many other spanning sets. Okay, we don't need to see more than this here. Okay. At this point, I would like to give you those couple of definitions that we need to do in the theorem. So we know that. Yeah. Sorry, the punchline. I forgot the punchline. So the question is this P3 finite dimensional? Yes, because we have a finite set that generates it, or it spans it. Okay, so we say that it's finite dimensional. That's okay. Is finite dimensional. Okay, let's see an example of an infinite dimension, of something that is not finite dimensional. Okay, so let's consider the set of polynomials of any degree. Okay, I'm not going to put any bound on the degree. Okay, so in fact, this could be, I think it is PR. Okay, so let's take this example. Okay, so I'm going to do the same thing. I'm going to check that I can do so let's take PR to be the set. Sometimes also this is also written as, you would write it like this. Okay? R acting on X. Yeah, that's the standard way of writing the set of all polynomials, okay, of any degree. Okay, in an indeterminate X. Okay, so it's a set of guys called P or P of X. Okay. Of the form such that P of X is of the following form: I goes from 0 to n. I'm going to call them P just to connect this notation with this notation here. I'm going to call them P. I xi, okay, for some p0 en r, okay, and n naught, okay. So if you can write something as a linear combination of these monomials, yeah, up to a certain number n. Okay, so you don't go to infinity. Okay, so you don't have power series. Okay, because otherwise you will get power series, which is also in space. Okay, I'm not going to do that here. Okay, I'm going to stop. Okay, then you call this the set of polynomials. Okay, let's check that this is indeed a vector space. Can you add two polynomials of n degree together? Yes. So what is the degree of the polynomial, by the way? So I haven't defined that. Okay? So the degree of the polynomial degree of P, and Pi is the maximal coefficient for which Pi is non-zero. Okay, so it's the maximum of the i's, okay, such that Pi is not zero. Because here I'm not telling you anything about these PI's. It could be zero. Okay, so you could take Pn is equal to zero. And then nothing prevents you from doing that here. Right? What I'm saying here is you take the maximum of this set here. Of course, there's one set that is empty, okay, for the zero polynomial. If you take all of them to be zero, then this set is going to be empty. Yeah, so there's nothing in there. Okay, what is the maximum of the empty set? That's minus infinity. Okay, that's just by definition. Okay, so the degree of the zero polynomial is minus infinity, and the degree of all the other ones is 0, 1, 2, 3, 4. Okay, so for example, polynomials of degree 0 are constants. Polynomials of degree 1 are linear polynomials. Okay, degree 2 are quadratic. Degree 3 are cubic, etc. Yeah, what we never read. Okay, so this is just a way of formalizing. Okay, the sum of two polynomials is just to sum them together. Okay, so you just so this is basically by using the same convention there. Okay, where the PI's are the coefficients of the polynomial P, QI are the coefficients of the polynomial Q. Then the sum of the two polynomials is simply the sum of the coefficients multiplied by the numerals. Okay, and here we have to take the maximum of the two degrees. Okay, so we take the max of degree of P and degree of Q. Because it's clear that one of these ends that we can choose is the degree of the polynomial P. Yeah, so if you stop your summation at the degree of the polynomial P, you don't need to continue further, because you know that everything else is going to be zero, right? So that's basically what it is, yeah? And same thing here. So suppose you were programmers, okay? So someone tells you have to program a class. Have you done object-oriented programming already?
Yes.
Yes. So suppose you're asked to program a class that defines polynomials. Polynomials are very handy object. Suppose you were to do a library, a scientific computing library, okay, and you need to implement polynomials. Okay? So can you build a class whose objects are the polynomials? How would you do it?
An array.
Yes. Arrays. What's the length of these arrays?
Depends on the degree of the polynomial.
Exactly. So it's arrays of arbitrary length. Yeah. The length is arbitrary, but of course it's mathematically it's finite. Yeah. So that's what makes it easy to implement this. Yeah. Right. That's why you can implement it on a computer, because you know that it's finite. It might be as large as you want. Okay. It can be 100, 1,000, 1 million. Okay. But you know it's finite. Okay. So this sequence has to end at some point. So in fact, polynomials, in some way, in some very abstract way, are nothing but finite sequences of real numbers that obey certain rules. Okay, one of them is the rule of addition. The other one is the rule of scaling. There's the third rule, which is the multiplication of polynomials. Okay, but I don't want to worry about that now, because all I care about is the linear structure. Okay, for now I'm looking at the linear structure of polynomials. Okay, so I can sum them, multiply them. Okay, so this is a vector space, right? Because then you check that all the rules of algebra work properly for you. Okay, so this is a vector space. Can we find a spanning set for this vector space? And the answer is not really. You cannot find a finite spanning set, right? In other words, in a programmer's point of view, is can you put a number n that is the maximal length on your vectors? No, because you may always need to go 1 degree higher if you want to implement all the polynomials. If you're implementing polynomials up to degree 3, then you can stop, as we did earlier, right? So there's a fundamental difference between polynomials of a certain degree, maximum degree, okay, and polynomials of any degree. Okay, so the set of polynomials of any degree is really a vector space, but it's huge. Okay? It's really big. It's not really huge. It's big. Okay, so it's infinite dimension. Okay, so in this sense, it's kind of huge. Okay, but we'll see that there's vector spaces that are infinite dimension that are even higher. In some sense, they're even bigger. Okay, so infinite dimension is kind of like a bit tricky. So we need to understand finite dimensions first. Okay, but this is just to show you that there are things which are quite interesting in infinite dimensions. Okay, so finite dimension is not everything. Okay, so let's come back down to Earth. Okay, and look at finite dimensions and finally prove this theorem. Okay, so I'm going to do a lemma first. Okay, so do some lemma. This is independence. And finite dimensions. Or independence in finite dimensions. So independence can be characterized in finite dimensions. Well, it's not characterized, but it can be. There's a criterion, like a necessary criterion for independence in finite dimension. It's necessary, it's not sufficient. Okay? And it's just count the elements of your set. Okay? So suppose V is a finite dimensional vector space, is a finite dimensional vector space. Okay? You go and you look at the definition of finite dimensional vector space. I've erased it, okay, but you have it in your notes. And it says basically, it says that there is a finite set that spans this vector space. Okay, so that this finite set, let's call it W1, W2. So as usual, I'm going to write the span with, when I have a finite set, I write it as a matrix, as an array, which is a row of possibly columns if I'm in Rn, okay? But I don't need to be, so these do not need to be columns in general, okay? These are just like elements of some abstract vector space, okay? If we are in Rn, then you can think of them as being columns, okay? So my notation works both for abstract vector spaces and Rn, okay? So suppose this is the case. So V is finite dimensional, therefore there exists a finite set of generators, or a finite spanning set for the vector space V. Okay? So all elements of V can be written as linear combinations of these n vectors. Okay? And let, okay, so suppose another set, okay, let's call it V. Okay. So suppose V1 Vk is in V, is an independent system of set. Then K has to be smaller or equal than N. Okay, this is crucial. Okay, so that the count of guys that is independent cannot exceed that of a spanning set. Okay? And also, we have another conclusion here, is that we can write span, we can write V as the span of these guys here, and some W hat all the way to W hat n minus k, where these W hats are actually some of these W's. Okay? They don't need to come with the same index. So W hat 1 is not necessarily W1. It could be, for example, W2 or W3. That's why I'm putting a hat, because it's different, right? So these guys here are some of these guys here. Okay, so where W on is equal W here for some. Okay, so basically, this is telling you this practical words. It's telling you that you can pick k of these and you can replace them with V1, Vk. Okay, so it's like a replacement lemma. Okay, so I can replace. And in fact, this is the proof. That's how you prove this lemma here. Okay, is by replacing. Okay, so let's do the proof of this. A proper proof should be done by induction. Okay, but I'm going to give you the idea. Okay, by doing a bit of I prefer to give you an algorithmic instruction. Always prove by induction, because proof by induction sometimes may hide what's going on. Yeah. Then, of course, same proof works by induction. Okay. So let's do it. First, let's try to do it mentally. Okay, so before I write it down. Okay, try to follow it. Okay, so you start with this vector here, with this set here, set of vectors. Okay, and pick the first one, V1. If the set is independent, what do you know about V1? You know that V1 cannot be 0, right? Because if V1 is 0, then your set is not going to be independent. Okay, so this is a small property of independent sets. Yeah? You see very quickly that independent sets cannot contain the 0 vector. Because if they contain the 0 vector, then you're going to find a coefficient, say 1, and all the other ones 0. Okay, but the first one is not 0, such which nullifies the linear combination 1, 0, 0, 0, 0. Yeah. So you found already a solution to the linear system that is not trivial. Okay. So this one, is it clear what I'm saying? V1 cannot be 0. Is it clear? Should I repeat this? Should I write it down? Okay, it's clear. Okay, good. So V1 cannot be 0. So if it's not 0, and it is a linear combination of the W's, right? It must be a linear combination of the W's, right? Why should it be a linear combination of the W's? Because the W's span the space V. Okay, and V1 belongs to V, and therefore it has to be a linear combination. Right? Okay. Now the linear combination cannot have all the lambdas 0. Okay, mind you, the W1, Wn don't need to be linearly independent. Okay, they might be linearly independent. Okay, so this is not saying anything about the independence of the W's. Okay, it's talking about the independence of the V's. Okay, but the coefficients that are given for the V as a linear combination, for the V1 as a linear combination of the W's, cannot be all 0, because otherwise they would make the V1 0. So one of them must be non-zero, right? One of these indices j must be non-zero. Okay? And therefore, you can replace the corresponding w with the linear combination in terms of v1. Okay? And that's exactly how you're going to replace. So this replacement that I told you about here. Okay? So the ones that are remaining here are going to be exactly the ones that remain from this process of replacement. Okay, so proof. It's going to be, okay, so the proper proof is by induction. On K, on N and K. Okay, on N and K. Okay, so here we give the idea. So the idea is pick and replace. Okay, so pick and replace. That's the idea. Okay, so let V1 is different than 0. Okay, this is because we have by independence, because of independence. Yes? So check that you understand why I'm saying this. Okay, so if V1 is different than 0, also V1 must be equal to W lambda, okay, for sum. So this is just a quick way of writing lambda I W I for R going from 1 through N, right? For some lambda N in R, right? That's because V1 belongs to V, which is the span of W. Right? And therefore I can write it as a linear combination of the W's. Right? But now one of these numbers is non-zero. Okay? One of the lambda i's is not 0, right? Otherwise, V1 would be equal to 0. If they were all 0, then it would be the 0 vector. Okay, so one of them is not allowed to be 0. Okay. So let me call it like this. Let me call it W check 1. This is W I. Okay, so define W check 1 to be the WI, which corresponds for this lambda I, which is not 0, which corresponds to the one that makes V1 not 0. Okay? Say, for example, the smallest one. Okay? So you go through, if you had to implement this, okay, you would go through your in an imaginary algorithm, because it's like infinite dimensional. I mean, there's infinitely many choices to check from. Okay, but suppose you want to implement an algorithm, okay, you have to go through all the i's from 1 to n for loop, and the first one for which you find the lambda I is non-zero, and there must be one. Okay, you stop, and then you call that one the WI. Okay. Now what I'm going to do here is I'm going to replace this Wi by V1 and show you this. Okay, that the span of the following. So let me indicate the set W. Sorry, I'm indicating with this kind of curly but not calligraphic. It's kind of like it's curly W. Okay, no attention to it. So this is the set of all the W's. Okay, it's essentially the matrix W. Okay, it's the array W. Okay, but I'm thinking of it just as being a set, right? So I don't have to worry about the order where it comes from. Okay, and then I take out this guy here. Okay, I take it out. Okay, and then I add V1. See what I've done here? So I've replaced. Okay, so this pick and replace. Okay, pick. Replace. That's the idea. Okay, pick and replace. Yeah. So I'm picking and replacing this. So now my claim is that this is equal to span. This happens to be equal to V. Right? Because that's my assumption. Yeah. All right. So all I need to do is to show you this claim. Here's the claim. Is this one here? Okay. So understand that once I've done this, all you need to do is then repeat again, because then you're left with a set of V2 all the way to Vk, right? It's still linearly independent, because if a set is linearly independent, then a subset of it is also linearly independent. Okay, that's a nice thing to check. Okay, it's very easy. Okay, once you have that, then you go through the same procedure by replacing your W with the new one that you got here. Okay, so again in the same assumption of the theorem. Again, you cycle. Okay, and you go this way all the way up to exhausting. Okay, and you can do it because by induction you can show that the first part of the theorem. Okay, this one here is your inductive hypothesis. Okay, so you can do this proof in a nice inductive way. The important thing is to understand this procedure. Okay, this is why I'm doing it in this more intuitive way. Okay, so I'm moving in the way. Okay. So the only thing we have to do is still to check this. Okay, that's this time. Okay, so to show that, okay, so to show. Notice that one is easy, right? One inclusion is always easy. This one here this one is easy. That's by definition, okay? Because all these vectors are vectors of V, and therefore the span of them has to be in V. Okay, you cannot exit the space you started from, right? Okay, so this is clearly a subspace of V. Okay, what is not so trivial is to show that any element of V. Any element of V can be written as a linear combination of these guys here. Okay? I know already that any element of V can be written as a linear combination of the W's. Okay? So to show, we need to find. Let's call them mu's. Okay, so mu. Mu Rn such that any element of V can be written. So for any V, so, okay. So this is I should try to be better. Okay, I should say for any V we need to find for each V in V, we want to find a set of coefficients, mu, such that V is a linear combination of these guys here. Right? Okay? So when I do this, I'm going to call all the other one some other name. Okay? So we have to put a symbol on that. Okay? Say a bar. Yeah? Okay, so W bar 2, or actually let's check them. Let's check all of them. Okay, so we check, and then we call W bar 2, whatever is remaining, etc. Okay, so we renumber them. Okay, we relabel them. Okay, this is just like a very boring exercise. We label them. Okay, the important thing is that we have written W in this way. Okay, so we have W check 1. Okay, and this is what's remaining. Of course, the number has not changed, right? Yeah, the number has not changed. Okay, so this is what's remaining. And this one is I'm extracting out, okay? And I'm replacing it with V1, okay? So in fact, well, I have to do that. Okay, so let me, so I want to show that there is a set mu. I goes from 1 to n, okay? And here we have this, so I'm going to write from 2 to n with these w's. Okay, and the first one is going to be mu1 w, sorry, mu1 v1, which is the first one that I've replaced instead of this wi. Okay, that's what you need. Okay. So in order to do that, okay, so we know that v is already a linear combination of the lambda i's. The wi, this we know because it's a span. Okay, that's span assumption. Okay, and then what I need to do now is to replace. I isolate the W check, right? The W check 1. Okay, so I'm going to this is lambda 1 W check 1. Plus the sum for I from 1 from 2 to n of lambda I. I need to check these guys because I have to find the correspondence. Okay, where the corresponding lambda check is the one with the same index. Okay, and now this one here is nothing but a wi. Okay. And I know that the lambda I corresponding to this wi is non-zero. Therefore, wi, this one here, I call it I. I shouldn't have used I anymore. Okay, so I is frozen from here. So let me use another index for my i's here. Okay, we'll use j. Yeah. So j there, here's j. Okay, because the I is frozen. The I is a special one that happens to be lambda I non-zero. Okay, so this W check 1 is nothing but WI, which corresponds to that one which is non-zero. Okay, so in fact I can divide by it. Okay, and I can take all the V's, all the W's, okay, with their coefficients, lambda J, lambda K. No, K is not allowed because I'm using put the K there. I, J, K, L. Okay, so L W, L, and this one goes from. So this one is the one that is different than R. Okay? So I'm going to write it like this. Okay, so all the L's that go from 1 to n